Dear student of B Tech first year, I am Dr. Ravind Parsai, Associate Professor of Mathematics in Engineering Science Humanity Department at Chamidi Group of Institution Indore. I want to teach you through this lecture number 6, the legendary polynomials, Bessel's function of first kind and their basic properties. So, first of all, we understand what do we mean by legendary polynomial of first kind. A legendary polynomial is denoted by Pn of x of first kind and is defined by a generating relation summation n equal to 0 to infinity h की power n of Pn of x equal to 1 minus 2xh plus h square raised to minus 1 by 2. Now let me discuss a particular example based on this concept here. So prove that Pn of 1 equal to 1 and Pn of minus x equal to minus 1 raised to n of Pn of x. Most fundamental property or example on this legendary polynomial is this question. So very simple, we will solve this question as follows just by using this recurrence relation or generating relation here. So we know that a legendary polynomial Pnx is defined by generating relation sigma n equal to 0 to infinity h की power n Pn of x equal to 1 minus 2xh plus h square raised to minus 1 by 2, call it by 1. Now our objective is to find first result. So for this we are putting on the both side of this equation x equal to 1. So put x equal to 1 on the both side of this equation 1, we get sigma n equal to 0 to infinity h की power n Pn of 1 equal to 1 minus 2h plus h square raised to minus 1 by 2. Just solve this by an algebraic expansion a square minus 2ab plus b square. So square of square से power से cancel हो जाएगा. So this gives to you the power is 1 minus h raised to minus 1. We know that the series of this function here 1 minus x की power minus 1 की series होती है 1 plus x square plus x cube, that is 1 plus h square plus h cube dot dot dot. Now you can write this series in summation notation also in the next step, as left side is as it is sigma n equal to 0 to infinity h की power n Pn of 1, while right hand side you write as sigma n equal to 0 to infinity h की power n. Now on equating the coefficient on the both side of h की power n, we get Pn of 1 equal to 1. So left side the coefficient of h की power n is Pn of 1, while right hand side the coefficient of h की power n is 1. So that's why you are getting first result. Now we concentrate on the second result. Also we know that, or we can write as 1 plus 2xh plus h square raised to minus 1 by 2 can be written as in this series as by taking in this pattern here 1 minus or minus 2h into minus x plus h square minus 1 by 2, because we know that this is the generating expansion. This can be written as in polynomial as legendary polynomial. Just changes in place of x you are having minus x, you write as sigma n equal to 0 to infinity h की power n of Pn of minus x, call it by 2 by using equation number 1. Now we might write the same thing in another pattern here 1 plus 2xh plus h square minus 1 by 2 by taking h minus h here 1 minus of 2 into minus h of x plus minus h whole square. You are having the same thing, we can write here this expansion you also write in legendary polynomial forms as sigma n equal to 0 to infinity minus h raised to n Pn of x, call it by 3 again by using equation number 1. Therefore from equation number 2 and 3 we get, on equating them, because both are the value of the same expression here sigma n equal to 0 to infinity h की power n Pn of minus x equal to sigma n equal to 0 to infinity minus h raised to n of Pn of x. Now just by equating the coefficient of h की power n on the both side, before this you write the right hand side in the pattern as by taking minus 1 raised to n separately here, and so on equating the coefficient of h की power n on the both side we get Pn of minus x left side, on the right hand side Pn of minus 1 of Pnx, that is your the desired result number 2. Now we come to discuss some important properties of legendary polynomial as P and X here. So first one is the Rodriguez formula. So by the very famous scientist Rodriguez, who have been work on legendary polynomial, and they have been defined very easily the legendary polynomial. So 1 upon 2 raised to n of factorial n derivative with respect to x of the function is x square minus 1 raised to n, where n ranging over 0, 1, 2, 3 up to n. So when you put 0, you will get 0 order legendary polynomial. When you put n equal to 1, you will get first order legendary polynomial, and so on you can obtain here. So that's why you can do the self practice here by using this formula here, and by putting n equal to 2 here, you will get the answer is 1 by 2 of 3x square minus 1. And another important property is the recurrence relations. So this is the first recurrence relation, and this is the second recurrence relations, and one third property is very important, which we call as orthogonal property of legendary polynomials is just an integral property. We can say that when the limits are minus 1 to 1 and Pn of x whole square of x, this gives to you the value of this integral is 2 upon 2n plus 1 when m equal to n, and when m is not equal to 0, for all cases the value of this integral as definite integral is 0. Let me come to the another example in which we use the most important property of legendary polynomial as the Rodriguez formula here. So we know that, so this type of question in which you have to express a polynomial, any problem, any polynomial they will give to you to express in legendary polynomial. For this the best formula is Rodriguez formula, helps you in this such case. So first of all, we write the Rodriguez formula of legendary polynomial, or we can say that a legendary polynomial is defined by this formula as 1 by 2 raised to n factorial n d raised to n upon dx raised to n x square minus 1 raised to n dot dot dot. Since the degree of given polynomial is 3, first you obtain the value of legendary polynomial of third degree by putting n equal to 3 in these equations. So 1 upon 2 cube factorial 3. Third time you have to differentiate x square minus 1 whole cube of dx cube. So when you differentiate first time, you will get some result. When you differentiate second time, you will get some result. And when you differentiate third time, so this gives to you 1 by 2 5x cube minus 3x, very simple differentiation. Now from the above, you can obtain the value of x cube as 2 upon 5 of p3 of x equal to 3 upon 5 of x. This value you can substitute in the given polynomial of fx. So you will get this expression here, 2 upon 5 of p3 of x plus 3 by 5 of x minus 5x square plus x plus 2. Just simplify algebraically. So this gives to you first term having legendary polynomial 2 upon 5 p3 of x, then second term having minus 5x square, third term having 8 upon 5x plus 2. So still your polynomial is not completely reduced into legendary polynomial, so hence the further investigation is required. So that's why now we proceed to continue for finding the value of second degree legendary polynomial value here, again by using the formula number 2. So the second degree polynomial value of legendary polynomial is, since the value is second degree polynomial is 1 upon 2 of 3x square minus 1 by using the formula 1. So from that you are substituting this and then simplify this algebraically. You will get 1 by 3 as constant, 8 upon 5 as x, and this is the value of this as p3 of x minus 10 upon 3 of p2 of x. Now you have to write here, use the value of legendary polynomial of degree 1 as p1 of x. Since the value by formula number 1, p1 of x equal to x, and the constant polynomial that is p0 of x equal to 1, this value you will substitute in the previous one, you will get this expression. And now you can see these linear polynomial of various degrees as in graphical sense. So p0 of x is equal to 1, p0 of x equal to 1, as this is a constant polynomial, as b0 of x is y equal to 1, you can say that p0 of x is equal to y, and this is to be x. You can take here x is independent, this is along x direction, along y direction you are measuring the value of legendary polynomials. So this is the value of p0, and what will be the value of p1 of x? P1 of x is just like to a straight line passing through origin, that is y equal to x here, and so on. You can continue p2 of x here. So this is the graph of legendary polynomial of various order you will get. Now we come to illustrate the second function, special function as Bessel's function of first kind. This is defined as again by a relation as geometric expansion as infinite series. Jn of x equal to sigma k equal to 0 to infinity factorial of k minus 1 raised to k upon gamma of n plus k plus 1 x upon 2 raised to n plus 2 k. So now let me see an example on this method here. If you have to prove here Jn of minus x n of x equal to minus 1 raised to n Jn of x, where n is a positive integers other than 0. We know that the Bessel function of first kind is defined by this relation here, Jn of x equal to sigma k equal to 0 to infinity minus 1 raised to n upon factorial of k gamma n plus k plus 1 x upon 2 of n plus 2k, call it by 1. Now on putting n equal to minus n, because we need the result of this type of here, so everywhere you are putting minus n here in place of n, this gives to you this value. Now put k minus n equal to s, so that k equal to n plus s in the above equation. You will get j of minus n of x equal to sigma s equal to 0 to infinity minus 1 raised to n plus s, so gamma of s plus 1 x upon 2 of minus n plus 2 n plus 2s. So now just by separating minus 1 raised to n, sigma s equal to 0 to infinity minus 1 raised to s upon that this equation factorial of gamma of s into factorial of s into gamma of n plus s plus 1. How can you reduce into this pattern here? Because we know that most important thing is n is positive units are already given here. So there is one relation between gamma function and factorial function is gamma factorial of n equal to gamma of n plus 1. For this we are using this formula here. Gamma s plus 1 can be written as in factorial notation here of factorial of s, and gamma n plus s can be written as factorial n plus s can be written as in the gamma form as gamma of n plus s plus 1. So that's why, so this gamma s plus 1 is reduced into factorial notation, and this factorial notation is converted into gamma form here. Why we are doing this job? Because our objective is to convert into our standard pattern here. That's why the right hand side can be written as in Bessel's function of first kind as Jn of x by using 1, hence prove this result. We come to some basic properties of Bessel's function here. So one of the properties, orthogonal properties, just like to be legendary polynomial as we have to discuss here. 0 to 1, here the limits of integration from 0 to 1 x jn of alpha of x jn of beta of x of dx, this value is equal to 0 when alpha is not equal to 0, and when both are same alpha equal to m, then the value is 1 by 2 of j square of n plus 1 of alpha. And now we are obtaining the particular values of the Bessel's function here. j0 of 0 equal to 1, j1 of 0 equal to j02 of 0, and so on. You can continue this. Let me see the plots of or the graph of j0 and j1 are given in the following figure here. So graphically we can find this. We are measuring along x direction value of x, along y direction you are using measuring the value of Bessel's function of first kind here. So this is the value of j0 of 0 is 1 maximally, and then when you are increases the value of x, then the value of Bessel's function in decreases, and when you are taking the value of x increases, this value you are getting the value of Bessel's function negative, that is in downward sense, and so on, increases then decreases. So they are getting, this is the graph, as just matched to cosine function. So J0 is matched with cosine function, and while J1 of x is matched with sine function, because this is to be originate from origin. So this is to be increases, and when x is increases, this value of J1 is decreases. Then when this is to be decreased and this is to be 0 at this x equal to 0, when it is increased, the value is also increased, and then it is to be again in a downfall manners. So this is the collaboration of sine wave and the cosine waves you are getting here. Thanks.